Oh, um, be live. Um, okay, I think we should be good. Okay, I'm just gonna get started. So, um, this is gonna be a level maths revision session for the paper tomorrow. I have gone over past papers 2018, 2022. Some good questions in those. But I'm not going to go over past paper now. For A, I well imagine most of you should have done most of them already. And B, I don't want to take up the time, right? I don't want to do like a full 2 hour thing, 75, 100 marks. So I've compiled what I've done with this, and the aim for this session is I've looked at the past papers and I've compiled basically the same sort of questions that come up every year. And actually, these questions aren't too bad. I'm not gonna lie. I'm not gonna lie. Not that sounds a bit bad. The questions I don't think are that bad. They're fairly standard sort of questions. I assume the last few days you've probably been looking at the hardest, like A star, fucking like university level sort of questions. That's not necessarily there is a nasty parametric integration at the end if we have time. But the aim of this, especially when it's 9 o'clock now, and if you watch this tomorrow on the day, I kind of want to ease it in a little bit, and I want to go over the standard questions, so you know what on the day. Okay, these are like these questions say similar to what I saw yesterday or whatever. I know how to do this, because these questions will probably come up every pretty much in one of your two papers. And that's what I'm gonna do. So these are 75 marks of worth of questions, but the last one got 10 marks. So if we don't have time, it's only at 65. But I do want to go over it. Um, but these are the sort of questions we get, and you can see the first one already. If you've not tried that already, but I will say as well, I do predict the last question is going to be a nasty calculus question. That it tends to be that for paper. Well, not in paper one, but in general. For paper one, it tends to be like a different nasty differentiation or integration question. And at the end of this, I picked the nasty integration one. So make sure you know your calculus. Well, you should know it anyway. But I do predict that will come up. Um, so yeah, I guess that would be a good thing to practice in general. But I'm going to go over these questions then. We'll stop off with it. So, and also if you are interested in the questions, I should say, I've given the where it came from. Most of it's actually from 2022, because it's kind of recent. So I don't know. Um, maybe it looks similar to these questions, but anyway. And I'm stop off with it. So let's have a look at this question one. Very, very, very classic factor theorem question. A nice one to ease us in. You'll probably see that start of the paper somewhere. So we're given a function and we say that x plus 2 is a factor of x, and we need to find a missing value. Extremely common, extremely typical. So you should know, and it's kind of giving you a hint here. We're going to need the factor theorem. So the factor theorem says, well, if x plus 2 is a factor of f of x, then that means f of minus 2. So when the value of x, when that bracket's 0, so x is minus 2, that has to equal 0, right? So this whole function equals 0. And that's what we're going to do. So we just substitute x is minus 2. And that's what we're going to do. So that would be minus 2 minus 4 of minus 2 squared minus 3 lots of minus 2 add k. Minus 42, and that has to equal 0. Let's simplify this with a calculator. Minus 2 minus 4 would be minus 6 of 4, which is 2 minus 2 squared, add 6, that would be 10, add k. minus 42 equals 0. Let's expand this out. So that'd be minus 16 minus 6k minus 42 equals 0. And then we can solve for k. So I guess 6k then, just do it a bit step by step. 6k would be minus 60 minus 42. That'd be minus 102. Therefore, k would be dividing that by 6, right? So you get minus 17. That seems fairly sensible, I think. Okay, so that's that for 3 marks. Again, that's the procedure. You just substitute the value that makes this bracket 0. So x minus 2, you flip the sign essentially. So f of minus 2, and yeah, then you can find a missing value. Okay, that's a nice question to ease us in. Oh God. Okay. Question 2. Okay, this sort of circle question is very common as well. So we're given the circle, they should look like this, and we need to find the centre and the radius firstly. Okay, well, you should know the general form of a circle, which is x minus a squared plus y minus b squared is r squared. This is not in this form here, but what we can do is complete the square on x and the y terms. So first of all, let's put the x's together. So x squared plus 6kx, and then the y term, so y squared minus 2ky, and then I'm going to say minus 7. Right, move the constant to the other side. That's what we're going to do anyway. And then I'm going to complete the square on all the y and the x and y bits. So x squared is 6kx, so x, and then you halve it, so that'd be 3k all squared, and then you minus this bit squared. It's going to be minus all 3k all squared, which would be 9k squared. Yes. And then you do the bits for the y. So then that would be y, and then half of minus 2k is minus k. So y minus k squared. And then obviously you do that squared, so minus k squared again. And that will equal minus 7. And so then let's get it in this form exactly. So we need to move all the constants to the other side. We are going to get x 3k squared plus y minus k squared. And then you're going to have, we're going to have positive 9k squared and another k squared. That's going to be 10k squared minus 7. And that is this form here. So therefore the centre, so here the centre of this, of a general form, would be AB, and the radius would obviously be the square root of the number on the right hand side. So the centre, so the thing to bear in mind here is you have to pay attention to the signs here. So here we have plus 3k, so the centre for the x is minus 3k. And because it's minus k here, it's going to be plus k. And that should be your centre. And the radius is going to be, r is going to be the square root, because the radius squared is this. So that just the radius is the square root of this. And that's all in terms of k. Okay, so that's fairly straightforward, hopefully. Now we're told, again, this is also very common. We're given the line of equation y is 2x minus 1, and it intersects the circle at, wow. Usually it's 1 point. Usually if it's a tangent or touches the circle, it's one intersection, 1 point of intersection. But here we're told it's 2. So we're going to need to consider that. But because they intersect, well, what you should normally do really is equate them together. So we have this expression here. We call that expression 1 for the equation of the circle. We also have y is 2x minus 1, which is 2. So therefore, we're going to sub this equation of the line, which is 2, into our circle equation, which is 1. And then we're going to get x plus 3k squared plus y, which is now 2x minus 1 minus k all squared. That's going to be 10k squared minus 7. Now we're going to need to expand the brackets. So I'm just going to do this, but if you're having a bit of trouble, do it on the side. Okay, so x plus 3k. But this bit I can do. So let's say that will be x squared, and then 3k times x, and then that'd be another one, so 6kx. And then that'd be 3k all squared, that'd be 9k squared. And then we have to expand this. Now this I will do, just for the sake, because it's a bit more of a complicated expansion bracket because it's 3 terms. So this is going to be 4x squared. So multiply if we've got 2x first of all, everything on that bracket, and then it'll be the same with minus 1, and then k, minus k. So that's what I'm doing. So 4x squared minus 2x minus 2kx. Then I'm going to have minus 2x plus 1 plus k. Then I'm going to have minus 2kx plus k plus k squared. And I can simplify this, I think, to 4x squared minus 2x minus 2x is minus 4x. Minus 2kx minus 2kx minus 4kx. Add 1. Add k. There's a k and k, so that's plus 2k plus k squared plus 1. So now I've expanded that, I can just put that into here. So it'd be 4x squared minus 4x minus 4kx plus k squared plus 2k add 1. And I'm going to move it the constants back. So then I'm going to say plus 7 minus 10k squared equals 0. And then I just need to tidy this up. So first of all, put all the x squared terms together. So it's x squared and the 4x squared. That'll go to 5x squared. And then I'm going to bring all the x terms together. So this is going to, we have a 6kx here, so 6k. And then we have a minus 4x, that's minus 4. Minus 4kx, that's minus 4k. Then we have, and that's it. So really this simplifies to 6k minus 4, that's going to be 2k, right? I feel like I'm missing one. I don't think so. Don't know. So that'll go to 2k minus 4. Okay. Lots of x. So that's the x terms together. I feel like I am. I don't know why. Because this is a multiple. I don't know. I must be paranoid. X squared, 6kx, minus 4x, minus 4k. Yeah, it's simple. I don't know. I guess that's it. And then we add the constants together. So then we have k squared, add 2k, add 1, add 7, minus 10k squared. And then we have a 9k squared, remember? And actually, k squared and 9k squared is 10k squared, and that would cancel the minus 10. So that will all be erased. And then we're left with this. 2k add 1 add 7, that's going to be 2k add 8. Right? And that will equal 0. And now this looks like a nice form. This is now quadratic. Hopefully you can see with coefficients 5, 2k minus 4, and 2k plus 8. And that's what we're going to do. Oh God, didn't mean to do that. Now we need, the question said 2 distinct points. You should remember that means what? The discriminant is going to be greater than 0. Okay, so if we do that, then 2k minus 4 all squared minus 4, 5 of 2k plus 8 is going to be greater than 0, right? And then we need to expand this out. So 2k, that'd be 4k squared. I'm going to need more room here. I'll deal with that in a minute. So that'd be 4k squared minus 16k. Add 16. Yes. Okay, there. Add 16. And then I'm going to do, wow, this would be minus 20. That's for 2k plus 8. That's going to go to minus 40k. And then 20 times 8, that's going to be minus 160. So I'm going to write that up here. And that's greater than 0. And we can simplify this, right, can't we? Then that's going to go to 4k squared minus 16 minus 40, that's going to be minus 62k. Minus minus 144, greater than 0, yes? Minus 160 add 16 would be more minus 144. And so here we then get a quadratic. This is a quadratic inequality. You should be comfortable with this from GCSE. I think it's in the A level as well. But to solve this, we're going to need our critical value. So we need to essentially plot this quadratic graph to find the root. We need to know where the roots are. So so I guess the critical values, which come from solving this quadratic, they are k equals, and hopefully this should be right. 4 minus 62 and minus 144. Yeah, something's gone wrong here. I knew it. I knew something was off. Okay. What have I done? Do, 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 do. Okay. Plus 9k squared. Is that my expansion right up here? What should be me? I can't even expand a bracket. 2x times 2x, 4x squared, minus 2x, minus 2kx, minus a 2x, add a 1, add a k, minus 2kx, add a k, add a k squared. That should be fine. 4x squared minus 2x minus 2, that'd be minus 4x, minus 2kx, that'd be minus 4kx, add 2k, add k, okay, that should be fine. Just substitute it in, right? 4x squared minus 4x. Right, okay, that's fine. I think. What have I done here? Okay. 5x squared, plus 6k x, that would be 6k, minus 4k x, that would be 2k x, 2k, minus 4x would be minus 4. I feel like I'm missing another x, I don't know why. I don't know. And then a constant would be 9k squared added k squared is 10. But then the 10k squares disappear. Then I'm left with 2k add 1 add 7. That'd be plus 8. And b squared would be 4k squared minus 16k plus 16 minus 4 lots of 5 minus 20 of 2 minus 40. Okay, something's not right here. Let me check. By the way, you can check your k values right, because if you then substitute k back into your circle equation, or your line, well, the circle really, you should and if you substitute it to the line, you should get the same value, right? But if you don't, then you've gone wrong somewhere, like I have. Uh, no, that's fine. The quadratic. Let me. Have I inputted it into the calculator right? 4x squared minus 62 minus 44. Let me check this expansion. 2k minus 4. Cannot believe I'm doing this. So this is right. This equation is right, but I'm not getting the right values. I don't know what's going on. So that would be 4k squared, right? Minus 8k. And then minus another 8k. That'd be 16k. Minus 16k, which I've got. And then minus 4 times minus 4 is plus 16. So that's right. Minus 20. 4 times 5 is 20. 20 times 2, that's minus 40k. And then 20 times 8 is 160. So minus 160. Oh my god. You know what it is? What? uh, minus 40 minus 16 is minus 56, not 62. Where did I get 62 from? Uh, oh my god. Okay. Yeah, always check your answer. But you can check your answer though, which is what I did. And if you plug it into the values, you don't get the right solution. But okay, this should be right. And you should also, because I didn't get the exact values, which I think you need to get. I think the question said that, didn't it? So I got some decimal, so that can't be right, I don't think. So that's how I knew my answer was wrong. So I checked back. There's an exam tip there, but there we go. It's good we go over these. You know what I mean? It's good that I do it now rather than everyone else in the exam tomorrow. And it shows how you avoid my mistake. Check your answer. Make sure the answer makes sense. Because I've got a decimal, and obviously then you put that to the answer if you wanted to. You wouldn't get the right values. It wouldn't satisfy the equations. Anyway, let's solve that then. Hopefully this should be right now. Such a silly mistake. Uh, so funny. There we go. So we get K is 7 plus or minus root 85. We get an exact answer. Lovely. So one's negative, one's positive. So our graph is going to look like this. And obviously we want the bit of y is greater than 0 because that's corresponding. So if y is our quadratic, that's above 0. So it's going to be this part and this part, isn't it? Because everything in between is underneath the graph. So it's going to be k is less than 7 minus root 85, which is this value here. And the other value, k has to be above 7 plus root 85. And that is your solution. There we go. Got there in the end. Okay, question 3. But that's really what you should do. Obviously, the worst part of that sort of question is you need to check because you might be bound to slipping up like I did. There's a lot of algebra there, so be very careful. And like I said, you can check your answer if you're not sure. Anyway, so question 3. So logarithm again is fairly common sort of question with logs. They're assessing your log laws so you can like manipulate and stuff and simplify. And that's what's going on here. So part A is log 2 of root x. So there's really two main log rules you need to pay attention to, and that's log of a to the n is n log a, and also log a b is log a plus log b, and there's also one when you subtract as well. You'll see that in a minute. You divide. But these are the main, like these are the two sort of things to look out for. If you're raising by power, or you have a product, or you're adding two logs. So here I can see that we're not adding anything, so we need to probably make an index, right? And I can see log 2 of root x is just going to be log 2 of x to the half. And then by this law here, we can bring that to the front. So it'll be half log 2 of x. And what's log 2 of x? Is a. So that's going to be a half a. And that's just one mark. Again, use the mark to guide you to see how much you need to do as well. So I didn't have to do much there. That's just one mark. Question 2. So now we have log 2 of x squared and 8x. So there's not really anything I can raise to a power. So I'm going to have to deal with some sort of product. And I can notice that x is a common factor. So I can factor it out to make a product. So that's going to be log 2 of x over x add 8. And now I can appeal to this log rule here. And that's going to be log 2 of x add log 2 of x plus 8. If I split that up. And I notice log 2 of x is a. And log x plus 8 is b. So this is going to be a add b. And that's it. Cool. Then part C is asking for log 2 of 8 add 64 over x. Again, can I raise anything to a power? Not really. So I'm going to need to deal with some sort of product. So I notice 8 is a sort of common factor here. So I'm going to pull an 8 out. So that's log 2 of 8, lots of 1 plus 8 over x. So then that's going to be log 2 of 8 plus log 2 of 1 plus 8 over x. I notice that this is a number we can evaluate because I notice 8 is a power of 2. This is log 2, which is 2 cubed, and then the 3 would go out. So then 3 log 2 of 2 is just 1. So it'd be 3. You can put that into the calculator as well. Alternatively, if you're struggling to evaluate logs like this, you could say, well, log 2 of 8 has to be some number k, right? That's what we're working out. If we then raised it by this base 2, so 2 log 2 of 8 is 2 to the k, but the log 2 and the 2 will cancel. It's like e to the ln x will cancel to just x, right? And that's in the formula book as well. If you remember that, then actually this is saying 8 is 2 to the k. But then 2 to the what number gives us 8? Well, it's going to be 2 cubed. And therefore k is 3, which is what we've got here. But that's just if you were struggling. But even then, you got a calculator. But you can evaluate logs like that. Anyway, we have 3, and then we have to deal with this bit here. So how do I approach this? Well, I think the best step now is probably just to, we can't really factor anything else out. We can't raise the power. So just deal with something inside so that we can add the fractions together. So it's going to be x add 8 over x. And I recognise we have an x plus 8 and x, so that might help. But now I notice we have a division. So I can actually subtract the two logs by this log rule here of log a minus log b is log a over b. So we've got a division, we can split the logs up. So we're going to have log 2 of x plus 8 minus log 2 of x. And then obviously log 2 of 8 is b, so it's 3 plus b, and log 2 of x is a, so it's minus a. And that's our answer. Cool. So yeah, you just need to be comfortable with logs like that. There will be like a question in whatever format where you need to simplify or do something with logs to get an equation or something using your log rules. But hopefully practice it shouldn't be too bad. But that's the sort of strategy there. Question 4. Okay, so this is fairly common as well, but it should be really nice if you practice it. Again, it's not supposed to be a particularly nasty set of questions, but the more sort of commonish. But I honestly, as you see the past papers, most of the papers, once you practice, the questions aren't too bad, if I'm honest. But we have this, so it's first principles, and we simply need to say, show that derivative of sine x is cos x, using first principles. And with first principles, you even need to differentiate a polynomial expressions, for example, like 3x cubed with first principles, or sine and cos. Most of the time, it's going to be sine and cos because they can actually tick box a lot of different things off. You can tick box you using trigonometric identities and obviously first principles, and like trigonometry and stuff like that, and differentiation of trigonometric functions. Okay, so we need to use first principles. So this is in the formula, but you don't have to remember this, or that's a good idea too. And it's here, and I've copied it here. So that's our first step. So if y, so if I call y, if I call this f of x sine x, then f dash of x by first principles is going to be lim, which is limit as h tends to 0, of f of x plus h. Now I need to substitute x plus h into the input, so that's going to be sine of x plus h minus f of x, which is just sine x, over h. Okay, so what's our next step going to be? We're giving you a hint, really. It says you can use the formula sine of a plus b. So it's going to be double angle, right? Sine of a plus b is a double angle, which I've copied here. Okay, and I've noticed we've got a double angle here, so that's the next step. It's kind of like expanding a bracket. That's typically what you want to do when you've got a double, an addition angle. So limit h tends to 0. Now sine x, if I substitute x and h into here for a and b, this will go to, if you follow the formula, sine x cos h minus plus, sorry, cos x sine h, and then you got the minus sine x over h. I'm sorry, I will be back in a sec. Hang on, I'll be a few minutes, but I'll be come back in a sec. But have a look at what you're doing next. Now I'm back. I'll have to go back in a sec. Okay. Okay, so what we're going to do next? Well, we expanded the addition formula. But now we need to use this because we're given this, and then usually we'll give it these results. And we need to kind of factorize and make a numerator look like this. So, first of all, we have to sine h. So let's deal with cos x. The only term with the sine h is cos x. That's sine h over h. And then let's deal with the next part. So lim h tends to 0. Cos h minus 1. So we have a cos h here. So we have the other two terms, right? But we have a cos h here, and but not here. But we have sine x on both sides. So we can factor sine x and say cos h minus 1 over h. And now I notice that this looks similar. So now I can evaluate the results, right? So sine h is h as h tends to what? So actually, first of all, before I do it, I can factor anything with x out because we only need to keep inside things with h in. If it's x, we're not doing anything to the x. So that's cos x, lim h tends to 0, sine h over h. Likewise, we can factor sine x here, and then lim h tends to 0, cos h minus 1 over h. And then I can use the results, right? But I'll be back in a sec. Massive apologies for that. Without, without going into too much detail, I have a little stomach bug. I'm trying to power through it. I was okay earlier, but yeah. Anyway, so we got to this point, so then we kind of rejigged our numerator using the results here, and now we can substitute our results in. Okay, so sin x over h goes to 1, so this limit will go to 1, and this limit will go to 0, right, because we're told that. So then 0 sin x is 0, then cos x1 is just cos x, and that is what we wanted to prove. Okay, cool. Let's try and power through this then quickly. So, question 5. This is the modelling question, right? These are also pretty typical. So, on a roller coaster, so essentially, I'm not going to read through it really, but we are given some model equation, and we need to use the information given to convert that into maths, which we can substitute into here. Okay, so what are we given? So part A, we need to find a complete equation. That means we need to find the missing values. That's what that means. So let's look at what we're given. So the maximum vertical height, so the max height is 60. So I'm going to say h max is 60. And what else have we given? The carriage starts a circuit at a vertical height of 2 meters above the ground. So even it starts at t equals 0, h is 2, and we also given the ground is horizontal, which basically just means the x-axis is the ground essentially, but that's kind of a given. So we've got 2 pieces of information, we've got 2 unknowns. I think we can do something with this. So this is very typical. Like, this is a quadratic modelling, and it's very, very typical. They give information about the maximum height or the maximum point and one of the other points or a root or something like that. But the maximum, you should notice this is in completed square form, okay? Oh, why is that important? Because you should hopefully realise that when you complete the square and the quadratic, it gives you information about the maximum. So, when this bracket equals 0, you get the maximum height. So this occurs when t equals 20, right? In order to set the bracket to 0. And then we can substitute that in. Well, we use diverse information. H would be a minus b, but the bracket goes to 0. So h would equal a, but we know the maximum is 60, so 60 would be a there, okay? Then let's deal with a bit of information. Well, we just substitute t0, h is 2. So then 2 would be 60, a would be 60 minus b, lots of 0 minus 20, so it's minus 20 squared. And then we expand that. So 2 equals 60 minus 400b. That's what 20 squared goes to. And then we can solve for b. So 400b would be 58. So therefore b would be 58 over 400. What does that go to? 29 over 200. There we go. Keep it in exact form. That's the best strategy. If it didn't tell you to round anything, usually you got to leave in exact form. Okay, just, I don't know, best practice. Okay, so I found all the missing values, but it says give a complete equation. So we need to restate the equation with the values in. So therefore h is going to be 60 minus 29 over 200 of t minus 20 squared, and that would be part A. Part B then says use the model to determine the height of the carriage above the ground when t is 40. So you just need to substitute t is 40 in, really. Again, fairly common. It's 1 mark. It's quite nice. Just a substitution. So h is 40. T is 40. So h we need to find would be 16 minus 29 over 200. 40 minus 20 squared. That would be well, that's going to be the exact same answer, isn't it? That we got in I think in part B, part A. Let me check though. 60 minus 29 over 200 of 40 minus 20 squared. Yeah, you get 2. Yeah, I thought as much. Determine the height of the carriage above the ground with T's 4. Guess it's 2. Okay. Makes sense because 40 minus 20, 20 squared. We got 20 squared here as well, so you got 2. You could have just spied that, I guess, really, if you wanted to. But yeah, 1 might just substitute. Anyway, that's part B. Part C. So, instead, they're giving us this new model. Again, this is also very typical. You're going to get a trigonometric modelling question, and you need to find missing values again. So here we have alpha and beta, and we need to use the same information to then find alpha and beta. So let's restate it. H is 29 cos 90 plus alpha. Again, we're given the information, remember, H max equals 60, which occurs when t is 20, and h is 2 when t is 0. So we need to use these 2 bits of information to find t and alpha. Okay. Now, what you could, if you wanted to, substitute again, plus beta, sorry. You could substitute both of these, right? Because you have 2 pairs of values h and t to get simultaneous equations. But I'm not sure if it would be that nice. What you instead need to realise is, how do we get the maximum value of h? And this is again very common. You need to realise that cos and sine, they're between -1 and 1. Again, think about their graphs. They're between 1 and -1. So that means the maximum value here, the maximum value is going to be this cos and this cos bit's 1. So it's 29 of 1 at beta. But you know h max is 60. So again, if we just substitute t20 into there, we would get 180 plus alpha, and then it's a lot messier. But here we can get rid of the whole cos bit, and that's what you need to realise here to avoid nasty simultaneous equations. So anyway, you get this, and then that goes to 29. Therefore, beta is going to be 60 minus 29, which is 31. And then we can use the other information, which should be a lot nicer. 2, which is h, it's going to be 29 cos of 0t, 9 lots of t0. So 9 lots of 0 will go to 0. So you're just left with an angle alpha. Add 31. So therefore, 29 cos alpha is going to be 2 minus 31. That's going to be minus 29. Therefore, cos alpha is going to be -1. And then you just do the inverse, right? So alpha is going to be 180. You can spot that with the graph as well. Again, in between 0 and 360, it's going to be -1 at 180, right? But yeah, you could use the calculator for that if you want to. We're going to do another trig equation question later on, and you'll see. But that is your value. So that again, to find a complete equation, we're going to need to restate it. So it's going to be h is 29 cos of 90, add 180, add 31. And that's your value for part C. Again, very common sort of thing. You need to realise again, like with the quadratic modelling, you need to know completing the square gives the maximum or the minimum value. And with trig, the cos and the sine are between -1 and 1. So that the maximum value be 1 and the minimum be -1. And you need to pick whatever. So in this case, the maximum occurs when cos is 1. Okay, and that makes it a lot easier to work with. Okay, then part D says, given that the carriage moves continuously for 2 minutes, explain why the alternative model would be more appropriate. Well, they give us a number of 2 minutes, so t is in seconds, isn't it? Seconds. So if we substitute t is 120 into both equations, so the quadratic and the what's it called? The trig, you'll notice different things. But what if you could if you play it safe, you could substitute t is 120. I believe that at t is 120, you're going to get a negative value for the height if you use the quadratic model. So that's like it's going to be around here, right? And that cannot happen. So you could say something like, well, and then the other model will get a positive answer. So you could say one's positive and the one's. So you could say, for example, uh, t equals 120. The second model, the trig one, predicts a positive height. But the first one, which is the quadratic one, predicts a negative height, which obviously cannot happen. The second model is more appropriate, right? However, I think you should be fine with that. However, I'm going to double check that actually. Did I just? It should be because that's what the graph should look like. If you substitute, where do we get? Substitute t is 120 into that. Yeah, you're going to get a negative value, aren't you? 60 minus 29 over 200 of 120, sorry, minus 20 squared. Yeah, you get minus 1,390. Yeah, it's a big negative. Predict a negative height. I'm going to say minus 1,390. But what you could also say, you could just realise the fact that the first one's a quadratic, so it's going to have this sort of shape, like we just said. So it's going to be that sort of shape. But the what's it called? Because the second one, the trig one, is going to look like a cos wave. And also note it's going to be above the ground because 29 is less than 31. So we're shifting it 31 units up. So obviously if cos was -1, which is the lowest it can go, minus 29, but you add 31, it's still going to be at least 2 above the ground. So it'd be above ground, and it's always positive. And more to the point, it goes on forever. It's a cycle, right? And that's what's going to happen. It's a fairground ride. It's going to have multiple cycles, multiple revolutions, right? So for that reason as well, this second model, the cos wave, because it keeps repeating, it will be more appropriate because it's a ride that goes on multiple times. But this is a quadratic. It only goes up once and then it just loses its shape. So that's not reliable for that reason either. So you could say, I don't know, or uh, second model repeats itself, something like that. uh, or I don't know, is periodic or something like that, which is appropriate as the ride itself, right, repeats itself multiple times. So you can either or, okay, I believe. But yeah, those are sort of things you could do for that sort of question there. But I'm going to leave it there. Okay, question 6. So there are 10 questions, I think. By the way, but we'll see if we have time for the last one. But I do want to go to the last one. But question 6. So again, this is fairly common. Part A. Find the first three terms of ascending powers of x for the binomial expansion of this. Very, very common. Now, what I've also done, again, I copied the formula book, this section here. Wow, now we're going to need, well, which one are we going to take? This one or this one? Well, you should know that this one is the AS version, and that only works when you have a power that's positive integer. That's what this n means here. This n just means the natural numbers. That's 1, 2, 3, 4. So positive integers. But this one, the A2 version, this works for all real numbers of n. So if n's negative or fractional, it works for that, and that's what's going to happen. You're going to need to use this formula, okay? But if you're going to use this formula, it needs to be in the form 1 plus x to the n here. Hopefully you can see that. So we need to look like, remember, where are we at? Where's my pen? There we are. 1 plus x to the n. That's what we need to look like. But this looks nothing like this yet, does it? So again, the common thing you need to do with this is to use not log rules, index rules, third rules and whatnot to simplify this. So we can say 1 over root 4 minus x, that's going to be, well, 1 over 4 minus x to the half, right? Because it's a third. And then because it's a reciprocal, we can say 4 minus x to minus a half. And now we're in this form here, right? A little bit, right? The only problem is, again, you need to be careful. This constant must be a 1. It cannot be a 4. Okay, it has to match. So what we need to do is to factor a 4 out. Now, the best way to do this, before you confuse yourself, just, again, keep minus a half out. Don't do anything yet. Don't jump the gun. But we can take a 4 out inside the bracket. So it'd be 4 lots of 1 minus a fourth x, right? I've not took anything out of it, out of the whole bracket yet. I've just factored inside the bracket. Hopefully you can see what I've done there. So it's 4 lots of 1 minus a fourth x. And now this bit, 1 minus a fourth x, resembles this. Now, I need to take the 4 out the whole bracket. So now I'm going to apply the this index rule, where if I erase something, a whole thing by a bracket of the n to the power n, I'm going to need to times the powers, right? So a to the mn is a to the mn. And that's what we've got here. So that's going to be 4 to the 1, because obviously it has an index of 1. 1 times minus a half is just going to be minus a half. And likewise with this, it's going to be 1 minus a fourth x minus a half. Okay. And then this will simplify. You can use the calculator if you want to. But that'll go to just a half. Okay. Uh, cool. So we can ignore the half bit. We can times everything by half later. But now this bracket is in this form where x is, well, I'm going to use big X to make it different. Big X is minus a fourth x here. So that's what we're placing here. And our n is going to be minus a half, right? Our exponent at the end. Now, what we're going to do is use the formula for 1 plus xn, which is given here. So again, I'm going to say I need to substitute x is minus a fourth x in place of this x in here, and the n is going to be minus a quarter. And then it's just a matter of substituting it in. So it's going to be half lots of, and then I'm going to do the expansion, and it says to the first three terms of x. So the first three parts. So it's going to be 1 plus nx. Now nx. So what I'm sure what I'm doing here. I'm going to have 1, and then I'm going to do the nx. Now nx is minus a half. So it's going to be minus a half x. And remember x as well. So that's n minus a half. X is minus a fourth x. Okay. I'm going to make these signs a bit clearer. Minus and then minus. There we go. That should be clearer. So that's nx. Then I'm going to deal with the next part. So n times n minus 1. So that's going to be minus a half of minus a half minus 1. All over 1 times 2, which is 2. X squared. So that's going to be minus a fourth x all squared. And that's the first three terms, right? So that's going to be half of 1. And then minus a half minus a quarter x is going to be an eighth x. And then this bit will simplify to, minus a half minus 1 over 2 of minus a quarter all squared. That's going to be plus 3 over 128 x squared. Okay, and that's your first three terms. But then we need to times by half, right? So it's going to be half at a 16th x. Add 3 over 256 x squared, and that should be your final answer. Hopefully it made sense. It's a fairly common one, but it's just substitution, right? Once you make it, and the best tip of this is to be extremely clear with what you're substituting in. So like what I've done here, it's best to do that so you can make it very, very clear what you're substituting for x and n here. Okay. Part B. Okay, now we're given some stuff. We need to approximate this root 2 here. And we're given three possible values of x for it. And then it says without evaluating expansion, which means don't substitute stuff in. State which of the values of x should not be used. So when they say should not be used, that's basically saying which one's not valid, okay? And that's where you need to pay attention to this bit here. This series of expansion is only valid when the modulus of the x part is less than 1. So, but remember x here was minus a fourth x. And that has to be less than 1. And then that would mean, well, the minus will turn to a positive, so it'd be a fourth x less than 1 because it's the modulus. Therefore, x mod x will be less than 4 if we times by 4. Okay, and that's the domain of validity. So that is the values of x in this range. Remember, this means that x will be between minus 4 and 4. Any x values in this range, if you plug it in, it will converge to a number. If you put a number of x outside the range, and we're going to discuss a bit more of this in a second. Then if you plug the x in, it will not converge to a number. Okay, it will not at all converge to the bracket we have, like 1 minus the fourth x minus a half. If you plug a value of x in on the left hand side, this series will not converge to this number here. It will be completely different. So it will not be valid for x values above this. So let's have a look. So which of these is above 4? It's not 2, it's not minus a half, it's going to be minus 14. Obviously, mod x means plus or minus x. But, so x is minus 14 should not be used as expansion only valid for mod x less than 4. But obviously, mod minus 14, which equals 14, is greater than 4. So therefore we can't have that. So that's part I. And then part I need to charge. Then it said, and this is where it's really interesting. It caught a lot of people off guard, this, but I'm going to explain. Which I think will be quite useful. You never know what might come. So it says, given a reason, which of these values would lead to the most accurate approximation? So we dismiss x minus 14. Now we need to pick one of these two. Now, the answer to this will always be the one closest. So the the value of x that's closest to 0, right? In this case, it's going to be x is minus a half. As mod minus a half equals a half is closest to 0. Obviously out of 2 and minus 14, right? But you have to put that there. So that's your reason, but I'm going to explain why. So, this, again, we said it's convergent to the right value when x is less than 4. But there's also a rate of convergence. So when you pick values closer to 0, it's going to get closer and closer to the value that you want. Okay. Why is that? Well, when we pick values closer to 0, think about it. If you took 0.0001 to the 5 and 0.99 to the 5, you're going to very quickly see that this will be pretty much going to 0, right? But this will still be, well, what's 0.99 to the 5? It's 0.95, right? It's going to be very, 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 very slowly going to 0, okay? But with the same power of 5, this value, however, of 0.001 will pretty much be at 0, right? Extremely small values, a small value, sorry. In fact, this is actually, by the way, 1 times 10 to the minus 20. I just put it in. So there's a load of zeros, right? So this value is way more effective at going to 0 than this is. Hopefully you can see that. So the closer a value I pick to 0, the quicker we repeatedly we raise it to a power, it will go to 0 faster than a higher number. Why is that important? Well, think about it. Our series is essentially some multiple of x and then some other multiple of x squared, some other multiple of x cubed, and so on. With the argument I just said, because we are just adding more powers of x, forget the constants, they don't matter. If we have, let's just say, x add x squared at x cubed, x to the 4, so on. If we keep adding more terms to our series, when we pick values closer to 0, as we said, the powers will very, very quickly go to 0 if we pick a value close to 0. Like I said, x 0.001, that will make these terms vanish to 0 very quickly. But when x is say 0.99, it's still going to be quite a significant value. We can't just dismiss these powers because, like we said, x to the 0.99 to the 5 is 0.95. That's still fairly significant. If we have, so what that means essentially, when we have a smaller power of x, not smaller value of x and x goes to 0, we only need less powers of x. We only need less fewer terms before it just converges to the answer. Because if we add on more powers of x, they just go to 0 pretty much. Because this goes to 0 very fast as we raise by a power. But this, it takes a longer time, so we need more terms. So it's less effective. So the answer is, because of that, you pick the value closest to x to give the best approximation because of the fact it converges quicker to 0, okay, in the power of x. Okay, so that's the answer to that. Okay, cool. Question 7. Again, we have a modelling sort of question here. Again, very typical exponential modelling question. Again, I'm going to do part A here. So we're given n. I'm going to ignore the waffle. I know that n is a to the kt. We're given some information, 100,000 bacteria at the start. So n is 1,000. Yeah, number of bacteria is n. So n is 1,000. T is 0. And I also know it took exactly 5 hours for the population to double. So doubling is 2,000. And that means when t is 5, right? Now we just need to substitute again, like we did in the other modelling question, to find a and k, and then find a complete equation. So that's what I'm going to do. So let's substitute the first bit. 1,000 is going to be a e to the 0, but a e to the 0 is just 1. You can put that into the calculator if you want. So it's just a. So 1,000 is a. Cool. Then we also know 2,000 is a, which is 1,000 now, e to the 5k, because t is 5. So then I could divide by 1,000, so therefore e to the 5k is 2. Then I could take logs of both sides to say 5. I'll show this more clearly actually. Ln of e to the 5k is ln 2, but this 5k goes on the, again, it's a power, so we could take it out. So 5k ln e is ln 2. But ln e, again, you can put that to the calculator. Ln e will go to 1. So that's saying that therefore 5k is ln 2. So k is going to be a fifth ln 2. And therefore we found our answer. So therefore, I'm going to put this here. N is a e to the kt. That's 1,000 e to the k, which is a fifth ln 2t. And that's your answer. That's the model for 4 marks. Okay, then it says, hence find the rate of increase in the number of bacteria in the population. It's exactly 8 hours from the start of study. So we need to find the rate. So dn by dt. So how do we differentiate an exponential? Well, obviously we have a constant outside. Let's keep it at 1,000. But then we have sum of e to the kt. If we differentiate e to the kt, be times by the derivative inside the exponent, kt just goes to k. So we have to times by k. So it's going to be 100k e to the kt. But we know what k is. It's going to be a fifth ln 2 t. So this is going to be a fifth ln 2 as well. So therefore we can simplify this a little bit. To say, well, we could do 1,000 divided by 5. So that'd be 200 ln 2 e to the fifth ln 2 t. So then it says that t equals 8. So t equals 8. The rate dn by dt is going to be 200 ln 2 e to the fifth ln 2 of 8. And we just plug that into the calculator. and you get this number here, 420.2458, blah, 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 blah. What's it say? Give it two significant figures. Well, the first two significant figures 42, so 420 to two sig figs. Cool. So hopefully that wasn't too bad. See what? So that's the key, right? You just got to sift through the waffle and pick out the numbers, right? Which we've done here. That's what the method, right? Don't get bogged down by all the words. Then we're given the number of bacteria in the second population to be this, but K has the same value, okay? So and then T is the time again. Given that at T, capital T hours after the study, the number of bacteria in the two different populations are the same. So if they're the same, that means this has to equal this, right? These two equations. So that's what we're going to do. So we're going to set AE to the KT. It's going to be 500, was it? 500 e to the 1.4 KT. Okay. And we need to solve, and this is capital T, right? Although it doesn't really matter. But they are equal when time is this value of T here. So we just need to solve this. And actually, before I substitute anything, I can immediately spot I can use log. Actually, no, let's substitute A in, right? So that's 1,000. Then I can divide both sides to say divide by 500 to get 2e to the kt is e to the 1.4 kt. Now what can I do? I can take logs on both sides. So the ln of 2e to the kt is going to be ln of e to the 1.4 kt. And then I can recognise again, I've got the log rule, learn AB is going to be, we can split that up to add learn A, add learn B. So that's going to be learn 2, add learn E to the KT. It's going to be learn of E. Well, actually, we can bring this out because this is all the power, isn't it? So this is going to be 1.4 KT, learn E, but learn E is going to go to 1, so we're just left with that. And therefore, then we're going to have learn 2, and then this will simplify again to KT. And then minus 1.4 KT equals 0. Then that means KT minus 1.4 is going to be minus 0.4 KT. It's going to be minus learn 2. Therefore, big T is going to be learn 2 over 0.4K. So that's learn 2 over 0.4, 0.4, but we know what K is. Remember, K was a fifth learn 2. And you put that to the calculator, although you should be able to spot how it simplifies, but you can just put that into the calculator. Learn 2 of 0.4 of a fifth learn 2, and you get 25 over 2. Hang on, is that right? 0.4. 2/5. Yeah, that should be right. So you get 25 over 2, and that is your value of T. But remember, what is that in unit wise? The value of T, it's in hours, right? So it's going to be at 12.5 hours. Okay, cool. Okay, question 8. I'm going to do 2 more now because it's got live stream bugging. But I have done. I'll explain it as when it comes to it. Okay, question 8. Again, this is very common, at least for paper 1. I've noticed every paper 1 has some sort of like hardish integration question and A2 integration question. So substitution, you'll buy parts and stuff like that. I kind of gave it away there. So we need to show that this integral gives us this, and it's very common. They will ask this. So again, you need to brush up on your integration. But yeah, in recent years, they asked for substitution, so I think they're going to ask for a by parts question. But you need to remember all of them, really. And actually, in the formula book, they give you it. This is integration by parts. They give you it. They don't call it anything, though. But you need to recognize it's integration by parts. So you sort of need to know the formula, but they do give it in the formula book if you get like an exact, you know what I mean? If you get like a particular part of it. If you reckon that this exact expression is in the formula book, so you don't have to memorize it, but you kind of do because you need to realize this is integration by parts. They do not tell you that in the formula book. All they do is in the integration section, they give you a load of integrals, and then they just give you this. Like, oh, if you haven't learned it, you're like, oh, what is this? This is by parts, okay? And that's what we're going to do, really. So this is by parts because for two reasons. First of all, we have obviously two products of x, but more particularly, we have a logarithm. You should realize when you have a logarithm, you're gonna have to do by parts, right? That's how we deal with logs. And yeah, so as you notice here, we're gonna just basically substitute stuff into the formula, really. So we need a u and a dv by dx. So what will happen is the u will differentiate to du by dx. So we need to pick a number. We need to pick something that will differentiate. Uh, and what is the rule for that? The rule of what you pick to differentiate the u value here, it follows Lie8. Okay, that is logs inverse trig algebra or algebraic expressions. So that's just your polynomials and stuff like that, right? Your trig and your exponentials, okay? That's the order which you pick to differentiate, okay? But here, logs, we have a log, ln x. That's going to be our first order. The x cubed would be the A for algebra. It's an algebraic term. Um, so that's going to be our u, is ln x, which we're going to differentiate to 1 over x. Now, even if you weren't entirely sure of the order, it will take more time. But if you did it the other way around, you'd probably realise I can't do anything here with this next integral. So you'd think, oh, let's do the other way instead. There's only two possible ways of picking stuff for this, right? So one way doesn't go particularly nicely, try the other. But in general, you should remember Lie8, okay? That's the rule that you pick for your U value, you pick to differentiate, okay? So you kind of, I guess you could kind of think of it as dilate, right? Di for differentiate, for the Di, and then Lie8 for the order which you pick to differentiate. But yeah, so that's it. So that's a d dx. Then dv by dx then has to be x cubed. So therefore v is going to be the integral. So the integral of x cubed is a fourth x to the 4. Don't add a plus c here because we're going to have you don't need to do it here. So take the integral, right? So that'd be a fourth. So what you do here, obviously, you add 1 to the power. So you go for x to the 4, then divide by the power. So 1 over 4. And that's what we get here. Okay, well then it's just a matter of plugging stuff in. So the integral of x cubed ln x, that's going to be uv, that's going to be a fourth, oh, x to the 4 ln x, minus the integral of v, which is a fourth x to the 4, of du by dx, which is 1 over x, dx, okay? I should have put a dx there, shouldn't I, really? And then this goes to a fourth x to the 4 ln x. And then I'm going to take a factor of 4 out. Of a 4 quarter, sorry. Of a fourth. Well, x to the 4 over x is x cubed dx. And now you can see why we picked it the way we did. Because that now will integrate what we did earlier. So it's going to be a fourth x to the 4 ln x minus a fourth of again, that's going to integrate to a fourth x to the 4. And that's going to go to a fourth. x to the 4 ln x minus a 16th x to the 4. And that's it, right? Actually, we can factor this out, I guess. So we could say 16th of 16th x to the 4, sorry, of 4 ln x minus 1. But you don't have to do all of that because that's our integral, right? But we have a definite integration, which means we integrate with a limit. It's between e squared and 1. So that means the integral between e squared and 1, x cubed ln x. So we worked out the general integral. Now to integrate it with a limit, well, we're just going to apply the limit, right? So it's going to be a 16th. I'm going to factor the 16th out, actually. So it's going to be 1 over 16 of x to the 4, 4 ln x minus 1 between e squared and 1. And now at that point, it's just a substitution exercise. I'm going to do it over here then to make more room. So that's going to be a 16th of, and then you substitute the upper limit. So it's going to be okay, that's going to be e to the squared 4 of 4 ln e squared minus 1 minus, well, 1 to the 4 is going to be 1 of 4 ln 1 minus 1. And then that will go to a 16th of, well, e squared to the 4 is going to be e to the 8. So remember the log rule. No, not the log rule. What can you get log rule? The power rule. E squared to the 4. Wow, that's e to the 8 because of a to the m of n. You times the exponent, right? I didn't put that into the calculator. I'm not sure if the calculator will give you e to the 8 or it might just give you the decimal. But you need an exact number, so you need to realise that. So that's e to the 8 times by 4 ln e squared. Now we can bring the 2 out to have 4 times 2, which is going to be 8 ln e. But ln e goes to 1. So it's going to be 8 minus 1. And that's going to go to 7, right? But I'm going to leave it there now. I'm going to show my working. 8 minus 1 minus, now 1 lots of 4 ln 1. Now ln 1 goes to 0. Again, if you're not sure, you can just put that into the calculator. So that goes to 0 minus 1. So it's going to be minus of minus 1. Okay. And now this will simplify quite nicely. So we're going to have a 16th of 7e to the 8 plus 1. And I think that's all you can do with it, really. Let's check the answer. So the answer needs to be a in this form, ae to the 8 plus b. Well, okay, we need to split this up then. So that's going to be 7 over 16 e to the 8 add a 16th. But obviously that's a, and that's a b. And that's our answer. So again, that's really it, really, essentially. That again, remember we buy parts, it's given in the formula book, but again, you need to know how to use the formula. But and you need to remember this to know what to pick to differentiate. Remember dilate, okay? If you remember, you can actually get rid of the I. You don't need it for A level maths. You don't deal with inverse trig and integration. So you could just call it dilate exactly. If that's how it helps you remember. But you need to remember that though. Okay, we have a functions question. I'm going to try and whiz through this now. So part A, there's 2 more questions I want to go. This is one of them, and then we'll do one more, and then we'll leave it there. Because I don't want this to be too long either. But anyway, so part A, we have f inverse of 3 over 2. There's 2 ways of looking at this. So remember the inverse function swaps the xy rolls around. So xy becomes y to the x. So that means that input is essentially going to be y for the inverse. So this is saying this is equal to x. It's saying what value of x gives the y value of 3 over 2. So that's same as solving 8x plus 5 over 2x plus 3 equals 3 over 2, okay? Alternatively, and this is what I'll go over, which I think a lot of people go over, they use this approach. I'm going to write it here. You're going to just invert it from the general inverse. So again, I'm going to say y is f of x, so that's going to be y is 8x plus 5 over 2x plus 3. Now again, because the roles of x and y switch around, that's what we're going to do here. We're going to switch to x's in terms of y, and then that's our inverse. So y lots of 2x plus 3 is going to be 8x plus 5. Expand that out, so it's going to be 2xy plus 3y is 8x plus 5. Then I'm going to group with the x's on one side. So that's going to be 2xy minus 8x is going to be 5 minus 3y. So then x of 2y minus 8 is 5 minus 3y. Therefore, x is going to be 5 minus 3y over 2y minus 8. So now we've got x in terms of y. That's essentially our inverse then. So inverse 1 of x is now going to be 5 minus 3x over 2x minus 8. There we go. Now we've had an inverse. Now we just need to plug in 3 over 2. So f inverse of 3 over 2 is going to be 5 minus 3 of 3 over 2 all over 2 of 3 over 2 minus 8. And that, you put that into the calculator, you'll get minus the 10th. And that's part A. Cool. Part B. What's part B saying? Show that f of x can be written as this. So, there are two ways you could tackle this. You could actually just combine the fraction together to then say a of 2x plus 3 plus b over 2x plus 3. Okay, for God's sake. Plus 3. And therefore, you can say that this numerator uh, of a lots of 2x plus 3 plus b, that has to equal the numerator 8x plus 5. And then like with partial fractions, you know, you compare the simultaneous equations, you can do that there. So you can compare the coefficients of x and whatever, or you can let you can substitute particular values of x to get a and b. You can do that. That's not too bad if you feel too much. But I think what you should recognise is this needs to be divided because the degree of the numerator is at least the degree of the denominator. So it's a top-heavy fraction, which means we should probably divide it, right? Algebraic division. So it's going to look like this: 2x plus 3, and then 8x plus 5. Then how this goes is you want to times 2x by something to get 8x. That's going to be 4. So then you times that, so you're going to have 8x times 3 plus 4, which is 12. Then you take this all away. So that's going to be 8x minus 8x is 0. 5 minus 12 is minus 7. Therefore, f of x then, we got a number, a quotient of 4 and a remainder of minus 7 all over the 2x plus 3. And that is your value of a and b, okay? Cool, so that's part B. That wasn't too bad. Okay, now we're given some more information about other functions. And we're given a function g now. And it says state the range of g inverse. Okay, so you should notice again, because of the fact x and y switch around with the inverse, that means the range of the inverse is going to be the domain of the original function g. But we know what the domain is. The domain is the values of x we can have. It's given here. It's between 0 and 4. So there, and especially for 1 mark, we just need to state. You should recognise that this is going to be the range. So the range is simply 0 between g inverse of x between 4, not x, g inverse, right? That's a range. It's the function output we get, not the value of x. But yeah, that's really it. And then part D then says the range of f of g inverse. Now this you should recognize as the composite function. This is saying f of g inverse of x. Okay, it looks like this. They just forgot the brackets. Okay, that does not mean they're timesing it together. So what is this saying? Well, the range of it. We want the range of the whole this whole function here. Okay, so what this is saying is this input of f is g inverse of x. But did we not already see in part C, g inverse of x can only take between 0 and 4. So that means our input of f is going to be between f of 0 and f of 4. No? That's what we because g of inverse is between 0 and 4, so we need to consider the inputs between f of 0 and f of 4, and that will give you your range, okay? So that's what we're going to do. So f of 0, so I'm going to say f of x, remember, was, what was it? 8x plus 5 over 2x plus 3. Okay. So then f of 0 then is going to be 8 of 0 add 5 over 2 of 0 add 3. So that's 5 over 3. And f of what? F of 4 is going to be 8 of 4 add 5 over 2 of 4 add 3. That will get you 37 over 11. Okay. So you will probably be tempted to think, well, 37 is a bigger number. 37 and 11 is bigger than 5 over 3, so it's going to be between 5 over 3 of f of g inverse of 37 over 11. Actually, you'd be right. That is the right answer. Those are a range of values. But essentially, what you do need to confirm in your mind is if you are ever unsure, that's really what you got to do. You just got to think about the end values, okay? The two different end points. So here it's between 0 and 4. So you just plug in the end points f of 0, f of 4, and then that's your range. If you are ever uncomfortable with the range, you probably will get most, if not all, the marks for that. But if you're ever unsure, but so it's not always the case. But for A level, I don't think they'd be that mean. That's without a graph anyway. If they give you a graph, you do need to work with the graph really. Because obviously the graph will show you visually what the range of values of y are, which is your range. But anyway, in this case, we're not given any graphs, so they're not going to be too mean about the range here. But what we do need to verify to be completely crystal clear is essentially x is between 0 and 4. Cool. So 0's got what, like 5 over 3, and then f of, oh, that's 4. And then it's between 37 over 11. We need to confirm that really for any value of x in between, it doesn't like shoot up and then go back down. So there's an actual hidden maximum for the range, or vice versa. It doesn't like go down and then go up, which basically means we need to confirm there are no turning points, or we need to confirm, and this is a better way, confirm that it's an increasing function, which means that as you increase as the value of x goes up, the function keeps going up. So there are no dips, there's no turning points. So it just constantly goes up. So it's strictly between f of 0 and f of 4. But we can see it's decreasing because of what we got in part B. This f of x here is equal to, remember, 4 minus 7 over 2x plus 3. Part B will help us with this because what we're saying here is between x and 0 and 4, as we increase the value of x, this denominator gets bigger. So if So 2x plus 3, remember that's like a line graph. As x goes to as x gets bigger, so does the y value. So 2x plus 3 gets bigger. So that means if you're dividing by a bigger number each time, you get a smaller fraction. So that means as x gets bigger between 0 to 4, this 7 over 2x plus 3 gets smaller. But we're subtracting by this fraction. So that means as x gets bigger, we're subtracting by a smaller number. So the overall value gets bigger because then it's less negative. So that means as x gets bigger, the overall number that we get for the function is bigger. So it's an increasing function. So you just have to reason it like that. The alternative way would be to check there's no turning points, which you need to differentiate and obviously set to 0, which is going to be a bit of work. And between 0 and 4, you need to check there's no turning points in that range. So therefore, it's strictly increasing or decreasing, provided it's continuous, obviously. So there's two ways you can look at that, but most of the time it's going to be increasing or decreasing, which will allow you to simply conclude this, right? You get the two endpoints, and then you substitute it, and then you just get an inequality. But that's really all it is, essentially. If you ever stuck with that, I know range is a lot of people's like weak spots. I get that. It's very, very tricky. You do if you do degree level maths, you look at it a lot more extensively. Um, but yeah, you, you can just do something like that, and you probably pick up some of the marks. But anyway, that's to approach that question. So because what we said, the whole point was that because 0 was again 5/3, and then we saw the functions increasing constantly as x gets bigger. So it's just going to keep going up. And then when x is 4, you get the biggest value of 37/11. So the range is between 5/3 and 37/11 by exploiting the fact that the function is increasing as well. Okay, okay, this is the final question then, and then we're going to leave it there. And again, this is very, very typical again. Hopefully, you should have recognised all these sort of questions in the past papers. Okay. And hopefully, all these questions we're going over is to refresh your memory. Okay, so part A, I'm going to do it up here again. We need to show that 1 minus cos 2 theta plus sine 2 theta over 1 plus cos 2 theta plus sine 2 theta is identical to tan theta. So what we need to do generally is work with the more complicated side, then simplify it to get the more simpler side. And what you cannot do is do a bit of one side and then a bit of the other, and then you kind of mate in the middle. You have to completely go from one side and then get directly to the other without doing any more manipulation. So we have to leave this as tan and get tan from this, okay? So that's important, by the way. But yeah, that's what we're going to do. So that's clearly this is the more complicated side. Let's work with that. And I think the best way to start this is notice that we've gone from double angle to theta to theta. So really, we're going to have to do the double angle. This is why, again, I've copied the trig identities. Now, they don't give you the double angle, but you can quickly derive it if you do not remember them. Although it's a good idea to remember it. But, if you're worried or panicked in an exam, you've got, oh, God, how do I do 2 theta and so on? But very quickly, these identities are given, you can derive it. So, sine 2 theta is going to be sine theta add theta. So that's going to be sine theta cos theta add cos theta sine theta. Wow, we've got two lots of sine theta cos theta, and that's your double angle. Likewise with cos 2 theta, that's going to be cos of theta add theta. And then that's going to be cos theta minus the order matters here. So we have this weird minus plus symbol. That means whatever symbol you pick up here, you do the opposite, okay? So we have a theta plus theta here, so we need to do a minus. So it's going to be minus sine theta, which goes to cos squared theta minus sine squared theta. Okay, so those are you can quickly derive it if you ever stuck an exam using the information, the identities they're giving you. So we're actually going to use this then. So our double angle. So this is going to be 1 minus cos 2 theta, which is, remember, cos squared theta minus sine squared theta, plus sine 2 theta, which is 2 sine theta cos theta, all over 1 plus cos squared. Cool. Make it a bit clearer. Cos squared theta minus sine squared theta. And then add another sine 2 theta, 2 sine theta cos theta. Okay. So that's going to be 1 minus cos squared theta, add sine squared theta, 2 sine theta cos theta, over 1 plus cos squared theta minus sine squared theta, add 2 sine theta cos theta. So what can we do now? Now, you should really notice that and again, with these sort of questions with trig, you do need to remember your trig identities in the back of your mind. But I noticed that the Pythagorean one's staring at me. The cos squared theta sine squared theta is equal to 1. That you need to memorize, okay, or learn some way. Hopefully you should remember that by now. Hopefully, it's a very common one. And I noticed this because we have the sine squares and cos squares mixed up. I think we can use this. So, I noticed we have what? Yeah, I noticed if we this bit, I think I can deal with because this will go to sine squared theta. It's going to be 1 minus cos squared theta. So 1 minus cos squared is going to be sine squared. This is going to be sine squared. Add another sine squared. It's going to be 2 sine squared theta. Add 2 sine theta cos theta. And then I notice again have 1 minus sine squared. So in the same way, if I subtract sine squared to this, I'm going to get cos squared. It's going to be 1 minus sine squared theta. So that go to cos squared, add another cos squared, it's going to be 2 uh, cos squared theta, um, which comes from the 1 minus sine squared, like we saw here, that goes to cos squared, and then I've got this cos squared as well. So that's 2 cos squared theta, add the 2 sine theta cos theta. Okay, what can I do now? Well, I think I can factorise a sine on the top. Actually, I can divide everything by 2. 2 is a factor of absolutely everything. So I can divide by 2, and then I can factor by the sine. So sine theta of sine theta, add cos theta, over, and then cos is common on the bottom. So I can factor that out to say cos theta of cos theta, add sine theta. Well, actually, we have a common factor here. So you're left with sine theta over cos theta. And you should recognise that is tan. And there we go. Cool. Um, okay. That's part, again, that's very common. And part B, very common. We need to use this identity to solve something else. So, um, if you're ever struggling with this, where you've got different values of the angle, use a direct substitution to help you here. What's going on here? What is going on here? You can use a direct substitution. So, we can see clearly here that 2 theta is going to be 4x, right? Therefore, theta is going to be 2x. So, what we can do is substitute our theta to get x here. So, we know this whole thing here will simplify to tan theta, which should be tan 2x. Hopefully you see that right. So theta will be 2x, so tan 2x. So part B, tan 2x is going to be equal to, what did they give us? 3 sine 2x, okay? And now we just solve it from there. I'm also going to note the also the interval we're working in for x, 0 between x and 180, okay? Yes. And then we just solve it from there, okay? It should be fairly standard. And again, I'm going to need to bear in mind some of our trig identities as well. But there's not much we can do here, apart from realise that tan is going to be sine over cos, right? So it'd be sine 2x over cos 2x. That's going to be equal to 3 sine 2x. And then I notice I can then times by cos 2x to then get sine 2x is 3 sine 2x cos x. Then I can subtract both sides on both sides to then get sine 2x at minus 3 sine 2x cos x equals 0. Then I can factorise. What you should pretty much never do when you're solving equations is to divide, because you will lose, well, you might lose solutions. When you're using identities, it's fine because you're not considering solutions at that point. But when you're solving, you need to be very careful dividing. When you divide, you should instead seek to factorise. So instead of dividing by sine 2x, I'm going to factorise by sine 2x, okay? So that means sine 2x is a solution as well by doing that. So I'm not missing a solution there. That'd be 2x, wouldn't it? Not cos x, cos 2x. Make that a bit clearer. Then we get that equal to 0. So therefore, sine 2x, which is another solution we need, if you remember, is 0. Or, well, 1 minus 3 cos 2x equals 0, which means cos 2x. Well, 3 cos 2x is 1, so cos 2x is going to be a third. So now we need to solve both of them. Okay. So again, with both of these, with every trig equation, it needs to come down to solving sine of some angle theta equals a number, cos of some angle equals a number, or tan of some number of some angle equals a number. You can't really solve it if it's any other way. You need to boil down every single trig equation into this elementary sort of equation, because then we can solve these. Okay. Notice what we've got here. Cos of an angle is a number, and sine of an angle is a number. So now we are in a position to solve it. Okay. If you don't get it in that form, you need to simplify it to get to that form. But now we have. Cool. So 2x. So let's just consider the general sine graph of sine of x. So it's going to look like this. But remember, we're between 0 and 180. Well, if we're between x and 180, so therefore 2x is going to be between 0 and 360. So we need to adjust our range here. So we need to consider 360. So when is it equal to 0? Well, it's going to be here, here, and here. But remember, 2x cannot be 0 or 360 because it's a strict inequality. So the only values here, which is 180. So therefore 2x is 180. So that means x is 90 by dividing. Now let's have a look at this. So again, our cos graph is going to look like this. Okay, roughly. So a third is going to be about there, isn't it? So remember, we're going to have a solution there, and then a solution there. Okay, so the first solution will come from just from doing the inverse cos. Okay, remember it's in degrees because we're solving in degrees. That will be 70.52877 something. Okay. But then what about the next solution? Well, the next solution's here. And the way to approach this is to look at like the symmetry and like how the curve works. I notice essentially the distance between 0 here and this angle here, x, which is 70.5, obviously, that's the same distance between 360 here and this solution here. So what I'm going to do is, because the distance here is 70, this angle here, I'm going to take 360 away from 70.528, blah, blah, blah. And then if I do that in the calculator, I get 289.47122, blah, blah, blah. Those are two solutions between 0 and 360. If you are unsure as well with solving, you can check your answer by plugging this angle that we got into the cos of 2x. So that's going to be cos of the angle that we just had. So cos 289 gets us a third, which is what we've got. So that is the right solution there. Therefore, x then is going to be the half of all of this. So it's going to be 70 point two whatever divided by 2. And you're going to get 35.26. What does it say? How many significant figures, decimal points? To one decimal place. Okay, where appropriate. So that's going to round up to 35.26. We'll go to 3. Because now we start going from 2x to x. So we divide it by 2 to get just x. So you're going to get 35.3, and then this 289.47 divided by 2 gets us this number here, 144.73. Well, 73 will go to 7 to one decimal place. Therefore, x is 35 to 1 dp. So x is 35.3, 90, and 144 between 0 and x and 180. Because remember, that's 2x was 360 to x is 180 in this range. Cool. So that's how you solve that. That's the general process. Question 10 is 11. Sorry, that's the last question. I don't have time for this, sadly. More to the point, I don't want this to go over because obviously you have a very limited, precious amount of time now, so I don't want to waste any more time. But I'll give a general synopsis. So, first of all, I will say I did cover this question in my this was for June 2022, paper 1, and this is going to be my part 2 stream. That's on my YouTube channel and on my Twitch, but I don't know if that disappeared. But it's on my YouTube. It's on my uh, A Level Maths Past Paper playlist, and that will be on the very last question. I think it's like question 16 or 15 or something like that. I'll go over it in a lot more detail, but I don't have the time to go over it now, sadly. But I'd say in general, what you need to do is with parametric integration or differentiation with integration. It's very simple when you just realize how to convert between Cartesian to parametric. How would we express this area in just normal XY form? Well, it's going to be between, what's our limits? X is 0 and X is 4. Between Y, which is our function, Y is f of X, dx. So then what we need to do to do this form here with parametric integration, we need to just convert everything into t's. So first of all, x is 0. You need to then say, well, t, if you look at this, is going to be sine. Well, if x is 0, then 8 sine squared t equals 0, which implies sine t is 0. Then you get a solution for t. Likewise, when x is 4 at the upper bound here, again, you can say 8 sine squared t is 4. So sine t is going to be root of a half, right? Yeah, a half, yeah. And then you can solve for t that way, okay? And then and then that would be what the values you get for t here will be your lower and upper bound to replace the x. Remember, x needs to go to t, so you need to convert these limits into t. Then the y, well, y is here, 2 sine t plus 3 sine t. That's already in terms of t. So then you substitute the y bit in terms of t. That's just given. Okay, so I guess I could say y is 2 sine 2t and 3 sine t. You would put that in. That's cool. And then we just have this last bit, dx. Dx needs to go to dt. How do we get from dx to dt? Dx is dx. It's going to be differentiation. So we need to consider dx by dt. That's going to be what's the derivative of 8 sine squared? Well, we could say x is 8 of sine t squared. And then clearly that's going to be the chain rule, right? So that's going to be 8 of 2 times by the derivative in the bracket cos t, and then 2 minus 1. It's going to be sine t. 2 minus 1, which is just 1. And so that would be 16 sine t cos t. And actually that will go to 8 sine 2t. So that means the derivative is 8 sine 2t. Therefore, dx, if you times by dt, is 8 sine 2t dt. And therefore, you have everything now, the limits to y and the dx, all, I'll highlight it all for you. You have it all in terms of t, and then you just plug it all into the integral, and then you do some simplification to get to this. And then for part B, you then evaluate it, right? It's just an integral. Well, 8 you should know will go to 8t. 8 cos 4t. Remember, when you're integrating, it's going to be a positive sign, not negative. Okay, you differentiate cos to get minus sign, but not integrate. It's the other way around. So 8 cos 4t will go to minus 8 cos 4t. That's going to go to minus 2 sine 4t. Because instead of times it by 40, you divide by 4, not times by 4. So minus 8 over 4 is minus 2 sine 40. And then this bit, you should realise it's the reverse chain rule. So remember, the chain rule looks like this. Uh, remember, f of u times by u dash. Okay. Um, that's what happens when we so if we have y equals f of u, no, sorry, that'd be f dash. If we have y as f of u, then the chain rule dictates that the derivative is going to be in this form here. And that's the chain rule, okay? But here, we can reverse that and say, if we have an integral that is in this form here, then we can go backwards and integrate to get this original function. This is our trial function. And so 48 sine squared t cos t is in this form, because ignore the 48. Uh, um, we have u, which is sine, that's our composition. So it's going to be sine t squared times by u dash. Now u dash is cos t. So we have some function u squared. So obviously f dash of would be like x squared, right? Where x then would be sine t. And then we've got the derivative outside. So then the reverse chain rule again would say that the integral then, ignore the 48. So I'm gonna ignore the 40. Actually, I'll keep it there. Actually, nah, I'll get rid of it. Sine square t cos t. So then the integral again, then the integral is going to look like this. It's going to be f of u. Now remember, f dash was f dash of u was x sine x squared. So that's a u, if you will. So f of u is going to be sine x cubed, right? It's going to be a power 3. If you just integrate like like it's going to look like x squared, right? So the integral of that is going to be x cubed. Well, technically a third x cubed. So a trifunction is going to look like sine x cubed or sine cubed x. So if y is sine x cubed, therefore dy by dx is going to be, by the chain rule, 3 of the derivative inside, which is cos x, and then sine x, knock one off, it's going to be squared, which is 3 sine squared x cos x. And that's what we've got. We've got sine squared t cos t, sine squared t cos t, but we just got a 3. So we need to just divide by 3 to get rid of it. So then the exact integral will just be a third sine cube t. So that will boil down to, well, it's times by 48, so it'll be 48 over 3 sine cube t. And those are your 3 integrals. And then you just plug in your limits and then you work that out. But that's a general argument with that. I'm not going to go too much into that though. But like I said, I did go over it if you want to quickly look over it in my paper, my June 22 paper 1 guide. Well, not guide, but when I went over it myself, I went over this question at the end. Okay, I'm going to leave that there then. I don't see any questions or anything, so I'm going to quickly leave it there and then get this published on YouTube before well, before tomorrow. But yeah, good luck for any exams tomorrow.